So today we are going to talk about classification. Our discussion is moving away from regression, which we will be doing in the off and on, but uh, for classification, how it's different from regression and the same steps we did with regression to derive solutions for the optimal regression parameters from different angles, probabilistically and iteratively, analytically, we will see how binary classification can be attempted the same way. Previously, we looked at this design matrix of independent variables, M features, N examples, and we saw that they are all coming from real numbers. And the dependent variable y could have as many real values as many number of examples in the design matrix, rows in the design matrix. And we learned this function f given x will map from the m-dimensional real number space to the real numbers for y. And we learned that if there is a linear solution for such a problem, there are multiple ways to find the optimal weights for that linear solution, W transpose X. Now, the same design matrix, real numbers, and we will also look at the caveat of having a nominal variable in the mix as well. But the dependent variable is discrete. It can have discrete values, not real numbers. If there are more than two discrete levels in Y, we say multi-class classification. If there are only two, we say binary classification. What we are going to attempt is that this same W transpose X solution, is it workable for classification as well? In the first step, we will see, yes, the same W transpose X, if looked at differently, can give us classification with the different measures, not RMSE that we used in regression, but the same line can be now a classifier or classification boundary line. Data looks like similar to the one that we used for regression, but here, instead of looking at it as a continuum of one variable on x-axis and the mapping axis to the y-axis, what we are looking at is if there are two dimensions, input 1, input 2, and some of the data points belong to certain class, let's say red or 0, and the others belong to 1. So how a line can give us a separation. The same line, if we do regression, would come along. But we need a separator. So separator will also be a line. So we want to find a W transposed X, optimum W's that become a separator. So if there is a threshold, suppose we know that threshold, let's say 0. So if W transpose X is greater than 0, we get class A, otherwise class B. So looking at the same line differently can give us binary classification solution. All the points on the line will have 0 result, and for greater than 0 W transpose X will be class red, and less than 0 will be class blue. So it's a new geometric application and point of view of solving a different problem with the same regression equation. But we won't be doing regression here, even though we are using the line. How do we find out the optimal W's that give us this line? So graphically, W is this vector. And it's going to be perpendicular to the line that we want to draw between two classes. That's why the 90-degree angle will give us 0 W transpose X. All the points on this line, all the X values on this line multiplied by W, this vector will give us 0. Well, that's a beautiful application then for a line to be used in a classifier. That's why 50 years ago almost, this guy, Rosenblatt, proposed one of the first neural network ideas called Perceptron, where we have, if you notice, the design matrix. One example is on the inputs. So this one is the same added feature that we used to add in design matrix for regression. And here it's going to represent the same thing, the bias, and all other x values multiplied by some weights that we discover for regression in using least square or other solutions. But here we are going to do this iteratively, stochastically actually. So these w's will be updated with respect to certain error, and that error is, for a given example, if we multiply it with the w's and output is greater than 0 or less than 0, will represent the class 1 or 0. We compare this class with the actual ground truth class, output with the actual class, and if it's wrong, we need to do something, and that something is to change these weights. So this idea took the world of AI at that time by storm, and for a couple of years, Perceptron gave a great promise in the media buzz, just like deep learning these days. Interestingly, Rosenblatt's Perceptron's first implementation was not in software, but in hardware to separate apples from oranges or similar application. We initialize weights randomly or 0, 0, 0, 0. That's a choice. No difference. We reach to the same conclusion if there is one linear line possible between two classes. But what we do next is calc and classify. We calculate W transpose X. If the result is greater than 0, we classify it as 1, otherwise 0, and then we update our weights. For every example, we do this. So for ith example, we classify, and then we compare it with the ground truth. Hat is our estimate. Yi is ith class, ground truth. We compare. If it's wrong, we change W as much as the example. This is interesting point. Why this will work, I will explain, but this is what there is. So this guy is same eta that to have a sizable progress through the training, we can have it 0. We will learn nothing. We can have as 1. We will learn quickly, but usually it's a small number. For every example, we update the weights. Existing weight, we add as much as the amount of mistake there is. And voila, we get that. For this particular example, if I plot it and the simple algorithm, for every example, we are starting with here, randomly initialized weights, and you can see every new example wrongly classified changes the W. These two numbers represent W. W1, W2, W2 for input 1, W1 for input 1, W2 for input 2. And when we multiply it with the individual X points, X has 2 values, input 1, input 2. So when we start, number of errors that we make, 34, then 28, then 15, then 11, then 5, then 2, and then 1, and then we found the best separator and training stops. So as long as there is enough 0 error or tolerable error or enough number of epochs, number of times we pass the whole data set, training data set through the algorithm is 1 epoch. So if we get tired or run out of time, we can quit, or if the error is tolerable, we can quit. But As long as there is a linear boundary, Perceptron is bound to find that. How it works is if there is no error, the update will be 0. We are good with the weights. If the error is negative, so our estimate is 0, the actual value is 1, so we update positive 1 multiplied by xj. Otherwise, minus 1 multiplied by xj. So you can imagine this is just the direction of correction, and this is the magnitude of correction. In time, all the weights get pushed towards the appropriate class boundary, and we do this 1 point at a time. Geometrically, if we try to visualize, the W will pass through the origin and minus 0.66 minus 0.4. This is hand drawn, but the true one will be around here. And the angle of W with the class boundary is 90 degree. That's why all the W transpose X equals 0. All the points on this class boundary are going to give us 0 result. And if we expand this W transpose X, it's the multiplication of the cosine angle between W and X multiplied by the magnitude of W and magnitude of X. All right, what if we want to know the theta? Theta kept on one side, it's W transpose X divided by the magnitude of both. Whatever we get, inverse cosine angle of that number is theta. So W transpose X 0, we know it's going to be the class boundary, but we want to know and calculate the angle between these two to make sure that what we understand is right analytically. So this is going to be the angle. In that case, cosine angle, if we ignore this magnitude, is going to be not equal but proportional to W transpose X. As long as W transpose X is greater than 0, would mean that cosine of the angle between W and X is greater than 0, which means that theta is less than 90. And conversely, for the other class, the angle will be greater than 90. So visually, we can see all the points. If we take a vector for this point from origin to this point, less than 90 angle, and for the other class, for this client, this vector and the W vector will have greater than 90 angle. Interesting application of geometry and calculus to sort out two classes with the same line that we used to do regression with. Why it works? So let's look at the update rule. Wj is updated as much as this amount. And if we expand that, so let's say this is 1 or minus 1, we put plus minus here, and cosine of theta, since it is directly proportional to W transpose X, new W after update, and new W is equal to old plus xj plus minus xj, and we bring this X inside. W transpose X is the old thing plus minus something new, X J transpose the whole matrix X. On this side, we have cosine of the angle between W and X, right? So the new, whatever we have new is as much as this amount, right? W transpose X plus minus this amount. So the new angle will be either greater than the original W transpose X represented by cosine angle between W and X plus this amount. So new angle will be greater than this angle that we already had, or it will be less than this angle that we already had. How much? As much as this amount. So from two different angles, we now know how perceptrons created decision boundary can be a useful thing for binary classifiers. Analytically, we understand. Geometrically, we understand why it works and how it works. Then came 1969, and this book got published explaining why perceptron was useless. The cover of this book shows two classes, a binary classification problem that is not solvable by the perceptron no matter what, because perceptron assumes both the classes are linearly separable. And they are perfectly separable, otherwise perceptron will never stop changing the weights. The concept here I want to just drop in, we will discuss it again and again, the nearest point from the class boundary. Distance between the nearest point from any classes and the class boundary, we are going to refer to that as margin. So we assume that perceptron assumes that the margin is positive. So it's both the classes are perfectly separable. And third assumption is that the data is living in a sphere, right? In a hypersphere if it is multidimensional. And living with these assumptions is sometimes hard, but for many problems, we can assume and get good performance. The real limitation comes when for, let's say, this point and for this point, the class is 0. But this point is far away from the class boundary. This point is living right on top of class boundary or in the neighborhood, right? Almost less than one margin. What if we want to know not only the class, but the probability of belonging, right? Near the boundary points are equally probable for being in this class or that class. But perceptron just classifies. It doesn't give us the degree of belongingness. How about the categorical or nominal variables? We assume everything is real number, but what if? We often have categorical data. And as you can imagine, between these two classes, you can draw many interesting lines. Which one is better than the other? Perceptron just finds one and then quits. There is no mechanism we can measure that out of many possible lines, the one that is found by the perceptron is the best one. How do we recover from, how do we overcome these limitations? For that, we have a mechanism, a new method, logistic regression. But moving on to that, before moving on to that, I want to have some feedback from you.
So I had a question actually, if you could go back. So I was just wondering, could you clarify the hypersphere assumption a bit? What do you mean by that?
So if we take the norm of everything, there's going to be the same assumption that we had in regression. So number of, on x-axis we have, let's say, parents' age, on y-axis we have kids' age. Both are defined, right? We cannot have -10 height. We cannot have 200 feet height. So parents' height and both in the data that we can have for the variables is, if we take the norm of all the variables, it's living in a sphere, not beyond that. So we don't expect that data will, in the test data will appear out of that.
So it's like we can contain all of the data within like a certain radius about a given point?
Radius, yes, right.
Okay.
Even though we have limited number of samples, but that doesn't mean that when we have the solution, the test data will come out of the blue somewhere that is outside the norm of those examples that we already have. So sphere, I mean, when we take the norm, so we square everything. So within this box, we are making the model. Don't go out of the box for the test example. That this is what we are trying to say by saying that data is in the hypersphere. So examples are already limited, but don't bring a test example from somewhere like far-fetched example, right?
Okay. Yeah, this makes sense.
The parent's height, for example, if we put minus, then it's the regression won't work. Similarly, Perceptron won't work if it's the data is not delimited within the bounds. This is like one prerequisite for it to work. Other than that, I think the idea itself is simple. Update as much as the mistake it's making. So the amount of mistake is X. We can scale it with eta, but the concept is if there is a mistake, change as much as the mistake it is. And that is Perceptron and documented, implemented by Rosenblatt. He gave the name, we use the same name. But if you're curious about these 3 points, shall we move on to that before, if there is no question for the Perceptron? Dominique?
Yes.
So you agree that the estimate should be degree of belongingness, not just a plain label, right?
Yes.
In that case, I want to start with this example. Let's say we have one independent variable, number of hours studied, and the dependent variable is binary, pass or fail. So the students who studied around 10 hours, they're passing. And students who didn't study at all, 0 to 2 hours, they are failing. But many data points live in between, right? So drawing a line, stupid line like perceptrons around here or wherever will not explain the phenomena. For that, this kind of curve called sigmoid, because it looks like S line, it can solve our problem or this family of lines. So on y-axis, we map, for example, for 2 hours, we map the corresponding point for on y-axis. The probability to pass for studying 2 hours is about 0.18. And conversely, the probability to fail will be 1 minus 0.18. For this whole continuum, we can get the probability if we do it in this way. Interestingly, very interestingly, we don't need to move far away from the line equation. Same W transpose X, the line equation, if we put it in this equation, sigmoid form, it's 1 over 1 plus e raised to power minus W transpose X is this line, the sigmoidal line. In logistic regression, we call it the link function because it links linear line to the classifier, to the other domain where we have probabilistic interpretation of the classification result. We kind of transport from one domain to the other domain, the logistic, right? We transport result from one domain to the other domain. That's why logistic regression. Another solution for binary classification, and interesting thing that we can do with logistic regression is that the idea applies not only to real but as well as nominal variables. I will give a short example that you can also have a look later for the nominal variables. If we have this link function. Here, W transpose X is written in simpler line form, mx plus b. M is slope, b is intercept. We want to start with nominal variables. For nominal variables, the probability for an event of interest is number of data points for that event divided by total number of data points, right? For example, in this example data set, we have two variables, male, female, and the students in the honors program or non-honors program. This is the dependent variable. So if we look at the total, there are total 150 non-honors student, 49 honors student, total 200. So the probability for a randomly picked student to be in the honors class will be 49 by 200. All right, we keep this number, about 0.24, whatever, and then we try to reach to this number through logistic regression. N over N, about 0.24, 49 by 200. Now, if you remember, the definition of odds is P over 1 minus P. Probability of being in honors class divided by probability of not being in honors class. That particular odds, this number, P over 1 minus P, is actually e raised to power W transpose X. And we can change, we can get probability from odds by, this is the probability, this is the odds divided by 1 plus odds give us the probability. And if we expand it or solve it a little bit more, we get 1 over 1 plus e raised to power minus W transpose X. So 1 over 1 plus e raised to power minus W transpose X is actually giving us the probability for being in class A or B. So what is W transpose X? Mx plus B is actually log of the odds. Log of M e raised to power mx plus b. When we take log, we get mx plus b, right? So log of p over 1 minus p for the nominal variable should give us the mx plus b. How? We can look at this particular example that we try to solve. If we want to create a logistic regression model without using any variable, then the intercept, we have no information about independent variables, just the dependent variable, and we want to find out the model parameters, W. Since we don't have any independent variable, there will be only W for ones vector and the intercept representing intercept, and that is minus 1.125. If we put minus 1.125 in the equation that we just looked at, we get 0.245, which is the probability. Could you connect? So overall probability of being in honors class, we can calculate with pen and paper, 49 by 200, but logistic regression way, we will get the same number. That's what my point here is. Log P of P over 1 minus P. If we put 0.245 divided by 1 minus 0.245, it's going to be the same thing that we got with logistic regression. But if you do simple regression with no independent variable but vector of ones, we will get 0.245 as the estimate for W, and 0.245 is mx plus b. So mx plus b divided by 1 minus, we get the intercept, which is log of odds. So both regression and logistic regression are connected through this equation as long as we are dealing with nominal variables. Now, let's look at the case of real numbers and the problem of estimating W's. In regression, if you remember, we did it maximum likelihood way. So let's do the same here. Linear decision boundary. So minus W transpose X or W transpose X, they are same as long as they are equal to 0. So the probabilistic solution we set up the ground by having labels 0 or 1 values. And then for class 1, we will represent probabilistically. Given x, what is the probability for y to be 1? Will be, this is sigmoid functions representation. You can use any other if you like, but it is same thing, 1 over 1 plus e raised to power minus w transpose x. When we input the w transpose x here, if you remember, for the perceptron case, we looked at w transpose x when it is 0, that is the class boundary. If we have 0 here, then the result for the sigmoidal equation will be 0.5. So greater than 0.5, we have one class, less than 0.5, we have the other class. Because we just looked at the inner workings of 1 over 1 plus e raised to power minus w transpose x. It gives us the probability, right? This thing for perceptron being equal to 0 was the class boundary, giving us the class boundary. Same class boundary when we put in the sigmoid equation will give us result greater than or less than 0.5, and we can then decide not only the class but the degree of belonging as well. On the boundary line, both the probabilities will be same. So being in class 1, in class 2 will be equal. 0.5 divided by 0.5, we have 1. And if we replace the probability with the corresponding equations, so 1 minus 1 over e raised to power minus transpose w transpose x is probability for class 0. We keep it here, and for the positive class, we keep it here. When we solve, we get 1. Why? Because e raised to power minus w transpose x, when w transpose x is 0, when we exponentiate something to 0, exponentiate to 0, power 0, we get 1, right? So things are perfectly connected now. For perceptron, we lived with only the plain class labels, but using this equation, we can not only give the class label, but as well as the degree of belongingness. We also have some flexibility of changing the threshold for class imbalance problems. I will continue from this point on for the same course of discussion, but class imbalance problem and the decision threshold is an important caveat here that we need to discuss from application point of view. So please remind me when we finish to touch upon that point, because for perceptron, it's a dumb number. Whenever it's 0, we are in class A or B, less than 0, greater than 0. But this particular thing, since it becomes a probability, now we can decide, depending on the problem, the threshold, is it 0.4, 0.3, 0.6? We can change it and get better results. But for now, keeping it 0.5, the design matrix and the dependent variable being discrete, having allowed to take values between 0 and 1, this is the thing that we have. How do we estimate W's now? For logistic regression, probabilistically, then we can have the same first try to reach the likelihood function. It's a binary problem, so we use Bernoulli distribution and the sigmoid function raised to power y multiplied by 1 minus sigmoid function raised to power 1 minus y. We know this from the previous sections when we open Bernoulli equation. So this is going to be very useful for one example. For all observations, we assume that every example is independently and identically sampled, so we can easily multiply all the probabilities to get the probability of y given x and w for the whole data set. Taking log of both sides, it becomes log likelihood. So the yi becomes, when we take log, yi exponent becomes a multiplier. This multiplication becomes a summation, this multiplication becomes a summation, and this exponent becomes a multiplier. So the best W's will give us the best likelihood. If that is the case, maximum likelihood way, we need to now look at our problem. It's not as simple as we did for regression. Here we have another thing in the mix. We are not working with W transpose X only. We are working with sigmoid function. So we cannot take derivative plainly of W transpose X as we did before. We need to take first derivative of W transpose X with respect to W, and then of sigmoid. So chain rule will be applied. So in 2 steps. So for derivative of W transpose X, we know that it is X. With respect to W, only X is the constant now, W goes. For the second term, sigmoid functions derivative with respect to W transpose X, we need to do it in a way that when we open this sigmoid function, 1/1 plus e raised to power minus W transpose X, it's inverse of 1 plus e raised to power minus W transpose X, right? And when we take the derivative, that -1 comes here, and here we add 1, so it becomes -2. Only this term is dependent on, so we take the derivative of this term, e raised to power minus W transpose X, again multiplied by this 1, -1. So the solution, further solution for these spread out terms will look like this. Further cutting it down, we come to this point, 1 minus sigmoid multiplied by sigmoid. First term, xi, second term, 1 minus sigmoid multiplied by sigmoid, third term. For the third one, now we are going to replace these with their partial derivatives. So yi here, log sigmoid's derivative 1 over sigmoid, and then from the chain rule we get to put these 2 terms here. Similarly, log of 1 minus sigmoid becomes this term, and since dx of that will give us -1, we put -1 here. And then from the chain rule, the other 2 terms. Other 2 terms we replace with their solutions that we arrived at in the previous slide. So for this one, we have xi. For this one, we have 1 minus sigmoid multiplied by the sigmoid function. Same here. Solving further will give us the differentiated log likelihood of the logistic regression as y minus sigmoid of W transpose X. But the problem here is that this thing is not a solution. It depends on W transpose X, right? So we are stuck. No solution here. So after differentiating, we are again depending on something that we are trying to find. And how to maximize that, so it's no-go. But still, this may be useful somewhere. So let's keep tabs on that. So the maximum likelihood function, we know it's the summation of these 2 terms. We agree that y multiplied by log of sigmoid and plus 1 minus y multiplied by log of 1 minus sigmoid. If we want to take the derivative, we get this. If we equate it to 0, the maximal point v will be on this solution of this. Let's use it somewhere, but this is not going to solve our problem of estimating W's. What's the other way if we cannot do things analytically? We do it
iteratively.
Right. So we go to gradient descent now. Gradient descent will have like 1 step at a time, either stochastic way or batch way, both same approach that we did with regression. And but the likelihood function is this one now. So very much similar to the perceptron, we initialize randomly, or you initialize with 0, 0, zeros. 0, 0, zeros can come randomly as well, right? So it doesn't matter actually. We assume that the weights are somehow we have those initialized with some sensible numbers. And if it never converges, we can always start with different. But what we do next is calc and classify. We calculate the degree of belongingness by putting W transpose X into the sigmoid function. It gives us what? The probability. The probability greater than 0.5, we classify as 0. Otherwise, greater than 5, classify the example as 1. Otherwise, 0. And the only difference is here, right? If you remember, this is the equation that this is the term that we received after differentiating the log likelihood function, right? Y minus sigma of W transpose X. Well, this is very much similar to perceptron, but we are looking at a summation. So Y actual value minus the estimate summed over all multiplied by X. If there is a mistake, only if there is a mistake, we are going to calculate the amount of mistake not as 0 or 1, but it will be between 0 and 1. 0 means no update. Between 0, greater than 0 and less than 1, the mistake, because sigma will return some number between 0 and 1. So that is kind of soft update, right? Not like perceptron, so update size 1 multiplied by xi. No, it's between 0 and 1, some number multiplied by xi. And then that's all there is. This is the update rule. And if we want to represent this in matrix form, we can say the x will come here, x transpose, and this minus will go in and make this term positive. So y hat comes out of the sigmoid, y hat comes first, yi, actual ground truth y's, will go after minus y, and x transpose y hat minus y. When you implement in the batch gradient descent for logistic regression, you will be doing this. X transpose y hat minus y multiplied by eta, an arbitrary number, will give us the new W. And if you want to have some sensible weights, you can penalize the same way we did in regression. If you remember, in ridge regression, we added this term, right? So lambdas divided by 2 and the magnitude of W. Oh my God. So since from the start, we are looking at W transpose X, and we connected it with the same regression solution we could solve classification problem with. If it is binary, even multi-class, we can use it for multi-class as well. Perceptron gives us 0, 1 only, but logistic regression is again based on the same W transpose X, but in probabilistic domain. So we put it in logistic function, 1 over 1 plus e raised to power minus W transpose X, this guy. And same regression is doing classification probabilistically for us now. The other way is, I mean, for the large data sets, this can give us some trouble, gradient descent. And anyways, the other option is Newton-Raphson's way. This method is the actually implemented method in MATLAB or Python or Spark, guys who, when you need to have some performance optimizations and work on large data sets. So IRLS is the solution most commonly implemented in libraries. It not only needs first derivative of the likelihood function that we have, it also calculates second derivative. So the general Newton-Raphson's proposal is that the new value of the weight will be as much as the ratio of first and second derivative subtracted from the previous value. And this is the abstract idea. How we apply it in iterative reweighted least squares, and why we call it reweighted least squares, because previous solution we looked at is iterative, right? So reweighted least squares, why? We'll find the explanation shortly. This particular matrix is what we are going to do extra than gradient descent. The same design matrix for the columns are the features, rows, and we calculate second derivative. So for the first variable, second derivative of its first derivative. On the diagonals, we have self second derivatives. On the other terms, we have with respect to the pairwise. So x1 derivative of x with respect to x1 and then x2 and so on, x1 and xn. In the second row, we will have with respect to x2 and then with respect to x1 and so on and so on. So the whole matrix of second derivatives pairwise corresponding to the design matrix is called Hessian matrix, represented by H. Very common notation that you will see in textbooks. H is giving us the second derivatives. If we could calculate that, we replace things here. So first derivative, we know the negative log likelihood function we just calculated for the gradient descent solution. And the second one is H, so we bring it for the numerator up and it becomes H inverse. And for the derivative of negative log likelihood, if you remember X transpose, y hat minus y, right? Here, this guy. We reached this guy when we derived when we differentiated log likelihood, right, from here. We couldn't find it useful at that time because it depends on W transpose X, which we are trying to solve for W, and the solution that we thought will lead us to W is again depending on W, right? So we left it there, but it was not that useless. We used it here in the gradient descent, and then in the Newton-Raphson's method here, we are using it by replacing the values for first and second derivative, and X transpose y hat minus y is for negative log likelihoods first derivative, and for H inverse we can do this. We expand this with the corresponding inner terms, and when we take the partial derivative with respect to W for this guy, it will lead us to putting X inside with both the terms. With respect to W, only this term depends on W. This is constant, so it disappears. We remain with sigmoid of W transpose X multiplied by X. So, yeah, we reached here, and H will be the sigmoid of our W transpose X, 1 minus sigmoid of this multiplied by Xi into X transpose. And this particular guy we can represent in terms of matrix like this. X transpose for this blue term. R is the weight that we are referring to in the name, iterative reweighted least squares. So these are the weights. It's a diagonal matrix that is giving us the weight with respect to given input, how much weight for the update that we want to change, how much for every input, when we make a mistake, we reweight the updates as much as this multiplication. We represent it with R multiplied by X. So X transpose RX, if we replace here like this, inverse, and this much is okay to update with IRLS, but we take it a little further, and if we expand this, we get this particular equation that is should be very much familiar. If you remember, X transpose X inverse. So here we have R, which is a diagonal matrix. So it doesn't matter. Output is X transpose X because these have only diagonal terms. Others are 0. The weight matrix. So X transpose X inverse, X transpose in Y. So R X W J will give us Y. If you remember, we called this equation the normal equation, right? We used it for solving the regression problem. So IRLS is bringing us to the same solution, right? That is interesting. So we don't need to go this far when we implement IRLS. This much is okay. So new weight will be changed as much as inverse of the Hessian matrix multiplied by the derivative of negative log likelihood, which is X transpose Y hat minus Y. But going one step further is for us to realize that even logistic regression solution from the starting point was very much depending on W transpose X, and when we reached to the conclusion, it became the normal equation that we used for regression. So essentially, we are doing the same thing for regression and logistic regression. One is the error is measured in terms of squares. Here we are measuring the errors in terms of 0, 1 summation Y hat minus Y, but otherwise all things are connected and same. So in summary, we have learned today Perceptron for binary classification, an interesting interpretation of geometry and application. And then we looked at the limitations of Perceptron and how can we overcome, or we found a better solution in terms of logistic regression, which gave us the probability of belongingness in addition to the label of the class. We tried to solve it through maximum likelihood, which didn't work out because the differential of the likelihood function depends on W itself. But we could do it through gradient descent and iterative reweighted least squares way. And hopefully we will know from now on what's going on behind the scenes when we run a line of code and get the parameters. So here, logistic regression not only give us the probability, but the individual weights have a meaning. For example, intercept will represent the odds ratio, right? So we learned that logistic regression is in reality ordinary regression, but we are using a link function or logit as a response variable. So W transpose X is put into the link function and we get probability. But that particular linear relationship between X and Y is transformed. And now what I want you to pay attention to the next power of logistic regression. Let's say we concluded these two W's. So we have just one variable, gender, and gender is nominal variable. So the weight for gender is 0.59828, and for the 11111 feature, we have augmented feature, we have the weight minus 1.47, the intercept. In case of Perceptron, this means nothing, it's just a boundary. But in case of logistic regression, minus 1.47 means something. It's the probability of male in the honors class, being in honors class, or the log of odds for a randomly picked male being in honors class. The log of odds will be minus 1.4709. And for the W for independent variable also represents log of odds. So we can verify this with the data set. For female in honors class, if you want to calculate the log of odds, P over 1 minus P, the probability will be 32 divided by 109 and 77 divided by 109, P over 1 minus P. That number we should reach to through the logistic regression solution, and that number is 0.59 that we get here. So the probability of female in the honors class is this one. If female gender is male, in that case, this will be multiplied by 0, and the probability of a randomly picked male will be minus 1. The log of odds for a randomly picked male to be in the honors class is minus 1.47. So looking at the data, you can see fewer males are in the honors class, right? Fewer emails compared to female. And the intercept, which also represents the participation of males in the honors class, is minus. So these are not just numbers, they have a meaning and connection to the context and data. Especially in case of nominal data, you will be able to interpret your model in terms of probabilities and log of odds very effectively, which is not available in other solutions like Perceptron. Over to you, Matthew.
Oh, I think you wanted to mention the class imbalance problem at some point. You told us to remind you at the end.
Right. For class imbalance, let's say we have 90% 1 examples and 10% 0 examples. Right? For that case, would it be justifiable to keep the threshold as 0.5?
I mean, I think you'd probably want a higher threshold there.
Right. So we need to, in practical applications, change the threshold, and that's why we have to have a probabilistic solution to decide which threshold. In case of Perceptron, I mean, we have no insight, right? We have no insight. So what I can do is that I will send you this link to maybe 5 minutes read, but I will go through it first. So let's see. If we have probabilities as a solution, how elegantly we can address the problems from the context. One of the important ones is class imbalance. So for the negative class, if we bin the probabilities, the distribution looks like this. For the positive class, the distribution looks like this. All right, we are happy with it. Let's say this is the best possible solution, logistic regression or whatever solution. But since we have probabilities on x-axis, depending on the probability, we say the person is in positive class or in negative class. But we have to decide on the threshold somewhere. If we cut off here, so beyond 0.5, we will have positive. Below 0.5, we will have negative. So we clearly see that these examples will be misclassified, and these examples will be misclassified. Negative will be classified as positive. These examples, positive but classified as negative. So we need to change this threshold. The safest one is around here, right? Beyond 75, positive, but many will be misclassified as negative. Only so true positive rate and false positive rate, we can, if we, for all thresholds, we draw it. It looks like this curve. On x-axis, true positive fraction of the examples, and on y-axis false positive. For every threshold, we have this dot. And when we connect those dots, we get a curve. Looking at this is what we call ROC curve, receiver operating curve. Changing this decision parameter will give us different numbers for FPR and TP and FP. So that number we plot and we get a curve. Let's say we have another model that give us these two distributions, another logistic regression model, or perceptron, not perceptron, logistic regression with different parameters. So here our stakes are high. If we put 0.5, we make too many mistakes compared to the other model, right? Too many mistakes. So we plot these two in terms of ROC curve, and not only we can compare model A with model B, we can also find the sweet spot for our threshold. So wherever, depending on the context, so class imbalance will give a different, very different ROC curve. And looking at the curve, we will be able to decide which threshold is better. So for majority class, we want to penalize those, and we want to give some space to the minority class to live and flourish, right? So we kind of adjust our threshold from 0.5 to maybe 0.75 or 0.8. But it will, looking at this curve, we will be able to better decide which point is better for a particular problem. So you can give this article a read, and this luxury we get only if we have probabilistic outputs from the classifier. If classifier is dumb, like 0 or 1, we cannot do this. Benjamin?
Oh, so with what you just shared, so how is it determining the threshold at all? I mean, with the second example, it's clear that like maybe 0.55 would be a better threshold, right? I mean, does the article talk about that?
Right. So the article is using code not in Python, but R code. It's letting you simulate the values, so you can simulate class imbalance problem, and then see the ROC curve. And when you draw that, you will see that if you keep 0.5, you do some something excessive to the minority class, so you want to change it to favor minorities examples so that they don't get penalized for being minority. You move the point towards upper side of 0.5, but where you want to go, when we draw that curve, we see that, oh, this is the justifiable point. Let's decide it to be here.
I mean, is there a condition for that point on the plot, like that it has like a specific derivative or something?
That's a good question. It's actually it's the cost of making a false positive or false negative mistake. So if the cost of misdetecting minority class is too high, right? So we, not in terms of the derivative, but all right, if we have no cost, equal cost for making mistake type 1 error or type 2 error, so the best point is this one. All right. If the cost is same, so the best point where you see the tangential point that is giving the optimal, like true positive rate around in this area, whichever threshold is giving this area is better, but all other areas are kind of giving some, are not justified, so they are kind of preferring one class over the other because of the number of samples. So if you take derivative, like draw a tangent, it's going to be so around this area. So again, we are assuming that this mistake and this mistake, true positive, false positive, are same. But if they are not same, we are more sensitive for false positives, then we want to improve that. We will go here. If we want to, we care more about true positives, so we want to increase them and don't care about false positive, right? But for your exact answer of your question, I will give you after finding out if there is a heuristic or exact number that we decide. But if you're familiar with R a little bit, you can change the configuration of samples here. Minority and majority, we can change number of samples and see how the curve look like. Or next time I will bring that curve for you to see how to decide.
Okay, thank you.
Other than that, we are good with binary classification, but today I mentioned a word margin. So the nearest data point to the decision boundary, the distance between decision boundary and the nearest data point, can we use it to find more generalizable classifier somehow? So next time we will look at using the margin to choose one of the best. There are many possible lines. Which one is the best one? How can we use margins to do that? We will look at that problem, but it will be just an extension of today. So today was the core. We will extend this discussion into a little bit more smarter classifiers that help us draw better lines between two classes using margins. Perfect. Thank you so much for